Ladies and gentlemen, this is Grayson Swan. I'm immensely proud of him. He's a down Mac guy. Yeah, that's right.
He made it through. Got away, guys. He got away.
He's a very successful renewable energy person.
World, so.
Works all over North America on gigantic wind projects and a variety of other things, I suppose, including storage.
Yeah.
And was heavily involved with the Tesla power pack install up in Elmsdale that we didn't go see today, but is like a version of what we saw at Emera, but call it 20 times larger.
Yeah, if you want, you can check out my YouTube channel. I walk around it.
There
you go. You were out in Elmsdale, were you?
Yeah.
Oh, cool.
And I'll show them some pictures of that on Friday and things too. Awesome. Anyway, take it away. Thank you for having us.
So, welcome everybody to Porters Lake. It's a 2-turbine site here that we built in early 2016, so it was the winter of 16. The site itself is owned by Wind, which is a community group. It's about 200 investors here in Nova Scotia. I work for Onewind, so we're a service provider, basically a contractor to the industry. We're based here in Dartmouth. We were a very small company and we've grown a lot in the last 5 years. So we're based here in Dartmouth, but we've got an office in Texas and a training center in South Texas as well. So the overall capacity of this site is 3.2 megawatts. So from an energy perspective, it's about 1,000 homes in the area. The turbines themselves are manufactured by General Electric. So GE is like I think number 2 or 3 in the world for turbine manufacturers. In my opinion, they're probably the best from an economic and operational perspective. So they're not real pretty to look at. They're not like a finesse style turbine like an Enercon, but when you look at cost and performance, they're very, very good. And this particular model, it's a 1.6 megawatt. It's by far the most common turbine, I think, in the world. I don't know if anybody can correct me, but there's something north of 20,000 of these globally. So there's a lot of mileage on the model. It's an 80-meter hub height. So when we say hub height, we're talking about the center of the rotor there. The blades are 42 meters each, so your total tip height's 122, 123 meters. And these 2 turbines will run through 2036. So they've got another 19 years. Am I off on that already? Yeah, 17 years of operations. So blades. So the blades, obviously there's 3 of them. In the industry, you refer to that as a set. So blades are always delivered in 3s. They're balanced in 3s. So your set number should always match. Our nominal RPM on this machine is about 17 at full power right now. It's probably turning 8 or 9 RPM. And if we're producing not much. And actually, this guy shut down right as we pulled in. So your cut-in wind speed's usually 3.5 meters per second or so. So it's a pretty quiet day. Each blade is about 5 tons, so 10,000 pounds. On the GE design, you lift the rotor as one piece. A lot of the newer machines, you're doing single blade installations. So you actually fly the hub and then you fly blades individually. So any questions on blades?
What's the material it's made of?
Fiberglass.
Great.
So a blade, it's kind of cool. Like if you ever get to work inside of a blade or see a blade get manufactured, it's more or less like a big box beam. And so there's what's called the spar, and that's on either side, and then the webs in between. So it's like a big box beam that just tapers as it goes out.
It's like the same way the aircraft wings are made of?
Yeah. Well, I think they're mostly aluminum and...
They are composite carbon nowadays. But,
okay. Yeah.
All days is aluminum.
So some turbine blades are starting to use carbon, but it's fairly rare. It's more expensive and largely not needed. You don't have mass concerns as much, I don't think.
Yep.
Yeah. You can balance. So in the manufacturing of the blade, there's balancing chambers along the length of the blade where you can add mass. And so you want to make sure that they're balanced. And so basically, if you have one blade go bad, there's a couple of different things that'll happen. One option is to take the other two off and put a full new set on. The other option is to get the original equipment information and get a third blade rebalanced to that machine. Yeah, but honestly, most manufacturers, you change all three. Yeah.
Sounds like how you deal with your car's wheels.
Yeah, exactly. Cool thing about GE machines, and you'll see this with Siemens and Vestas, two other really major manufacturers, they can be rebuilt like completely. So we could take this whole thing apart and put basically a whole new nacelle up there for not a ton of money. I mean, it would be a lot of money, but you could more or less have a brand new machine fairly quickly. And the components, like if you were to work inside the tower, a lot of the components are off the shelf. Gearboxes obviously are unique to that platform, but there's 4 different major manufacturers of gearboxes, so lots of opportunity there. The generators are pretty standard. These machines have Hitachi generators in them, but ABB, Hitachi, Siemens, all these guys make generators, so yeah, lots of opportunities to rebuild. So the next component outside of blades, which blades actually need a lot of maintenance too, and that's one thing in the industry right now. Blade issues are, I would say, the biggest issue. Rotors keep getting bigger, and I think people don't understand the conditions that they're seeing in really, well, throughout their life cycle, but also in really extreme weather events. And so, like, I was on a site in Texas in January, and it was a brand new machine. It was a 136 meter rotor, so the blades were 66 meters a piece or so, plus a hub. So really massive, like 66 meters. That's 2/3 of a football field, right? Yeah. So, anyways, the next major component of the turbine is the hub, and the hub is where your blades attach, and that's the rotating component. So, the reason that's important to make note of is that's how your blades pitch. So when we were pulling in, you can see this guy's pitched out right now. So inside the hub, depending on the turbine manufacturer, there's 2 kind of common ways to do it. Electric pitch, which is like a big slewing rim on the pitch bearing, and a motor with a pinion, or a hydraulic pitch. So they actually use hydraulic rams with more or less like a ball joint on the bearing. And so as the ram goes in and out, it just turns the blade. It's kind of hard to explain, but if you Google like hydraulic pitch wind turbine, you'll find some really cool videos and images that would show you how that works. General Electric uses electric pitch, so these are all electric pitch machines. Kind of really pitching for them because I like the machine. It's pretty funny when you go inside the pitch system. A lot of the components are like off the shelf. Like the motors are driven by actually a forklift drive. The batteries that are in the emergency pitch system, I mean, they're all just off the shelf components. So I really like it. It's cost effective. It's reliable.
I think we brought a lot of knowledge from the airline industry to here. Since
Yeah.
they need to control rope, pitch, and we somehow need to control those as well.
Yeah, for sure. The controller in these machines is the same. If you were to go to a natural gas turbine that GE manufactures,
Ooh.
a lot of steam turbines, it's the same exact controller, just different software. Yeah. So then the next one, so we've got the hub. It attaches to what's called the Nicell. So the Nicell is like the big school bus looking white box at the top.
Is it the size the same as this bus?
What's that?
Is that the same size as this bus?
It'd be pretty close. I don't know how long that bus is, but a lot of the bigger machines now, the nacelles are bigger than that bus. They're pretty impressive.
Yeah.
These nacelles are about 60 tons, and inside of them, the hub attaches to what's called the main bearing. So it's one big bearing, a low-speed shaft, and then a gearbox. The gearbox in this machine it's a planetary and then 2 helical stages. On bigger machines you'll see double planetaries. And then the output is anywhere from 800 to 1500 RPM on the generator. And that's just there's a fiberglass coupler between the gearbox and the generator. So it gives it some flexibility. In the event of a really big, like catastrophic failure or something, it'll fail at that coupler, so it'll save your generator. So that's the nacelle. Any questions on the Nicell?
For the transformer, I do believe these are quite large in capacity already. Is the transformers at the back of the nacelle?
So in this case, the transformer, everything in the tower is 690 volts.
Okay.
There is a small transformer down tower to give you 400, 230, 120. There's no 480 in these towers. So yeah, 400, 230, 120 down tower, and then we just send that up tower. So there's no transformers up tower.
Okay.
With the exception, the pitch system has a transformer set for each blade, just to get to a different working voltage.
You said doubly fed. What does that mean?
So most generators, or like most traditional generators, would just have a single source, like the stator might be outputting or taking power, like a motor or a generator. We're doubly fed in that we've got active power both on our rotor and our stator. So there's a slip ring on the back of the generator, like a big slip ring, a lot of power going through it, and it's feeding the rotor. And what that does is it gives us variable speed, because we need 60 hertz coming off that stator at all times, because we're feeding that straight to the grid. And so the rotor, depending on the frequency, and to be perfectly honest, as a mechanical guy, like, it's a lot of black magic to me, but the converter does some really cool black magic, and it lets you run the machine at variable speed. So like right now we're pushing 60 hertz to the grid, even though that generator is not turning at 60 hertz. If that makes sense.
Oh, so that's
Or some multiple of 60.
That's actually one of my biggest concern about how they regulate the frequency at 60 hertz. I
Yeah.
thought they have some kind of the VFD, which is they get a frequency from the.
They do, yeah. So that's in the down tower side here.
Yeah.
So we'll be able to look at that. It's more or less a VFD. Yeah, you got 60 hertz on one side, and you got variable frequency on the other side.
Okay.
And depending on the wind, you're gonna either bring your frequency up or down off the stator. So active power is either getting pushed or pulled from the rotor.
Okay.
So that's your nacelle. Your tower is the next major component. So the tower is more or less a big steel tube. Like there's in this case there's 3 sections. Some of the biggest machines that I've gotten to work on, there's 7 tower sections.
I think the Ellershouse have 7 sections and they're made of different materials.
Well, yeah. So Enercon and a few other manufacturers use concrete towers occasionally.
Yeah.
Most people are still using steel, even at the really high hub heights. The reason you have to go to so many sections on the really big machines is the wall thickness is getting so thick that the mass of the section becomes just unbearably large, and the logistics are the challenge. Like honestly, I think the biggest challenge for larger onshore wind turbines is going to be logistics around transport. Like getting components to sites is really hard.
Think about these big blades just go on a truck and want to go through those tight turns at the highway.
Yeah, so all the transport side's actually pretty cool. Like all the trailers are articulating, like their tailing trailers are able to steer as well as the truck to get around corners, things like that. Okay, so at the base of the tower is the down tower assembly. So that's where the converter system's housed. That's where all your main controls are. Upstairs there is controls for the pitch, there's controls for the yaw, all kinds of auxiliary systems. But downstairs is where the main controller is. So the down tower assembly, DTA, it's the converter system. It's a liquid cooled system, which is pretty slick. A lot of machines, maybe 5 or more years ago, would have used an air cooling system, and it creates a lot of reliability issues because you get a lot of dust and debris and things like that. So I'm a big fan of it. You've got your main stator contactor downstairs, so we'll shut the machine down. When we start it back up, you'll hear quite a number of things fire, but when it synchronizes to the grid, you'll hear that contactor close. And it's all 690 volt, so that's kind of the standard. Most wind turbine converters are 690. A lot of the bigger machines are going to a 12 kV stator on the generator, and that's when you have the transformer up tower. So Vestas is most common for that. If you go up tower into Vestas, the converter system, the transformer, everything's up tower. So the only thing going down tower is 12 kV. So we get to the bottom of the tower. You can see at the base a ring of studs there, and we'll get closer to look at all this stuff. But that's the start of your foundation. The foundation's a big spread footing, so I should know the numbers. I think the diameter of this one's like 40 feet or so. So when you're standing by the tower, there's a lot of concrete underneath it. And it more or less, I like to think of it as it's like a huge bedside lamp post. You know, your bedside lamp just has a big weight on the bottom of it. That's basically what the foundation is. It's just a huge mass of concrete that the tower sits on. You have to make sure that your subgrade's really competent ground.
Yep.
So there's a lot of work and effort that goes into that. Yeah, so then the final stage before we get to grid side power is the pad mount transformer. So that's on the left hand side. So that takes your 690 volts and steps it up to 12 kV.
Is that a 1.6 megawatt transformer? Is that in the cabinet?
It's 1850 kVA. Huh. Yeah, it's bigger. When you get over to it, it's a little bit bigger than it looks. But yeah.
We're still 300 meters from the tower.
Yeah.
We just marched.
And then basically once you leave the transformer, you go back underground to what's called the riser pole here. So you'll hear people call it, if they're on the utility side, they'll call it the dip pole because they're used to power going that way. Everybody in our industry calls it the riser pole because we're sending it back up. So we go through the riser pole. There's a grounding transformer that would detect ground faults, and then what's called a gang switch. So the gang switch, the reason it's called a gang switch is because you actuate one arm on it and it opens all three phases. And so you don't single phase anything. And then, yeah, we drove by all the collector, but the collector shoots out to the road. By the cell phone tower there, you see the poles that have some cones on them. So there's various equipment on those. The cones are there because birds like to build nests on them, so it can be quite frustrating to deal with, but we figured cones were the best way to deal with it. But there's metering and there's what's called a recloser. So anytime you're going to interconnect with the utility on a large scale, and whether it's a wind farm or something else, a recloser is like a really smart breaker is the way I think of it. It's going to detect things like voltage dips. It's going to detect phase-to-phase issues, those kinds of faults, and it's going to open to protect Nova Scotia Power's grid from our system.
I think
And-
the
and actually
electrical
members.
engineers probably know more than us on this.
Yeah, for sure.
There's a lot of measurements and controls they need to do to make sure a safe grid when there's all kinds of generation. So do not complain your next electricity bill is expensive.
Yeah, exactly. So any questions on the collector? I'm just kind of rambling here.
Like,
You must have something.
I'm thinking about, are these wires all go to which place they go to? Is that they go to the substation? Or?
So this site, because it's only two machines, it's distribution connected, so
Okay.
there is no substation.
Okay.
So we just tie straight into the distribution line, and
Yeah.
the homes right here would be the first place that would see our
For
power.
for the one in Ellershouse, it's they built a dedicated substation. For
Yes, yeah. A site like this is honestly pretty easy from a design and build perspective.
that. Really
because
easy.
It's not much road. There is no substation. The collector circuit's simple, and the turbines they go together like Lego. Like seriously, they stack together, and all the field terminations. There is some, but there's not a lot. It's pretty basic. So
Jerry rig everything.
yeah. So we didn't really talk about the civil side, but with any turbine site and pad, you're going to see what's called your crane pad, which is it's a little hard to tell, but basically we're standing on really competent gravel, and so you test this whole area before you lift components, just to make sure that you're settled and your crane's not going to shift on you while you're lifting, and then your laydown area You can see it's quite large here. We had the benefit of space.
Yeah.
Some sites you don't have that benefit, and that's when you start to get into a lot of single blade work. If you want to build a rotor on the ground and fly it as one component, you need a big area to do it. So if you work in like the Midwest or Western Canada, a lot of like farmers' fields and things like that, and so you wouldn't want to like plow out a huge area for that, and so you'll get into a lot more where you just pull the blade in and fly them up one by one.
First time to be in a wind turbine.
Use that ladder, obviously, pretty self-explanatory what that's for. On the ladder, you've got a safety cable, so this is what you're tied into as you run. And then this is what's called climb assist. So most machines have either climb assist or elevators inside of them. Elevators are fairly common. I think you're going to see them become less common in towers because all the regulations associated with them. So it's much better to use like a climb. This basically takes 80 pounds of your weight, and it makes it really easy to climb.
And the top is, I saw these plates. So this is one plate you can climb up and you can take a rest and continue, right?
Yeah, the reason that they're here is that you've got a flange there, and so with the flange you have to be able to bolt the flange together. So during install you need a deck. Outside of that, you really don't need a deck.
So what are these used for? I saw they're regular outlets, right?
Yeah, so your climb assist plugs into one.
Okay. Can you lift up one of the lighting? Yeah. So that's a regular outlet. While others are touring or playing, I flew my drone to get some aerial shots. Here it comes. They're starting to play flying plays.
What's that?
See there? Okay, so that's all.
Yep.
Okay, that's an extremely satisfying road trip here. Flying my drone there is just amazing. Yeah, and now I know where the Tesla Power Pack is, although it's small, it's a demonstrate project, but I could drive people there to take a look, to smash their head if they are renewable energy deniers. Anyway, I hope you learned something, and as always, may the engineering mind be with you.